Cool.
Okay, we'll go ahead. Thank
Awesome.
you.
Start. I don't think I need to introduce myself since Dr. Henry did such a wonderful job, but today I'll present my work that I've been working on the last 3 years with Pacific Northwest National Labs, namely improvement of Hanford waste vitrification algorithms with machine learning, uncertainty quantification, and gradient-based optimization. And I'll get into what each of those means throughout the rest of my presentation. I expect this to take around 40 minutes, but we'll see how long it takes. Let me go. Here's the agenda of what I'll be covering. First, I'll get into the context of the problem that I'm solving and the algorithms I'll be improving. We'll then talk about just the field of open source modeling packages and how that influences this project. I'll then get into my contribution to this project, which include integrating machine learning models into a low activity waste vitrification problem, and then alternatives for uncertainty propagation for these algorithms, and integrating machine learning into high level waste vitrification problems. And then I'll conclude. So I'll just begin with the introduction, context, and problem. As many of you know, there's a lot of waste stored in Hanford, Washington from decades of nuclear processes, mostly weapons development and other reactor things, and they have over 200 million liters of sludge, liquid, slurry waste stored in these tanks. I think there's around 180 tanks. And if these tanks were to leak, it could be an ecological disaster for the water table in the area. So the current conservation effort is to vitrify this waste by mixing it with plastic forming chemicals in a vitrification facility and then melting it and pouring it into canisters. They'll be in solid form. It can be stored safely for a few millennia. So my work on the algorithms that I'll be improving focus on the vitrification facility for both low activity waste and high level waste, and mixing, deciding the recipe to mix on how to mix the waste with the glass forming chemicals. And there's a lot of reasons to do this. I'll just mention the 3 primary ones. Number one, this project is expected to be very expensive and take several decades. I think they publish a report every year about how much they expect to take. So obviously there's the economics factor. Anything to make these algorithms, this vitrification process, more efficient will save years and perhaps potentially billions of dollars. Number 2 is any method developed to treat nuclear waste is just better for the outlook of nuclear energy. It solves one of the core problems with nuclear energy and just provides a better future outlook for that technology. And 3, the tools that I've developed to help solve this problem aren't just applicable to this vitrification algorithm, but are widely available for engineers and data scientists to use for similar problems. Now that I've introduced the problem and motivation, I'll start getting more of the specifics. This is kind of an overview of the process flow diagram on the left here, and just the algorithm on the right. This is just 2 parallel streams, but you can just focus on one, where glass forming chemicals, GFCs, are mixed with low activity waste or high level waste in melting-free preparation vessels. Then they're fed to the melter and poured into glass canisters. So the algorithms that mix these determine how much of each stream to feed to that melting-free preparation vessel to form a viable glass melt, which will then form a viable glass. The algorithm is in 2 main steps. This is a lot of steps, but I'll break them down into 2. There's first the optimization step, which decides the optimal ratio or recipe between all these streams. And then another important factor of this algorithm is the uncertainty and how it's considered within optimization. So the rest of the steps are used for uncertainty propagation, where the uncertain inputs of this system are propagated to the outputs, and intervals are used to then inform. And unfortunately, those 2 steps, optimization and uncertainty, aren't very compatible, so that's why there's an iterative scheme between them. And this is just done until it converges. And this is more in depth of the system about the melted feed preparation vessel. First, there's the mass balance. You have the streams coming in, such as the waste and the glass forming chemical streams. You also may have a retention factor, because some of the products may go off into off gas or precipitate, which makes this problem potentially nonlinear. There's also another important factor for the optimization problem is constraining the properties of this glass melt and this glass waste. This is traditionally done with statistical linear least squares models, such as partial quadratic mixture models, which have linear terms and quadratic terms. These are used to model properties such as electrical conductivity of the melts, viscosity of the melts, chemical durability of the final glass, such as consisting tests of various releases and a few other properties. In order for the glass to be considered viable, these properties need to be within constrained limits during optimization. Not only are these properties constrained, but there's uncertainty buffers for both prediction uncertainty of models and composition uncertainty from the step that I just previously discussed. This is a large system. About 64 components are tracked throughout the process. And there's a lot of around 180 non-zero inputs to the system. So it's quite a difficult process to manage and consider. Really quickly, I'll mention the baseline models, since a lot of my work is trying to find models that replace these. These are least squares-based models that use linear and selected polynomial terms. This is just the general format of them, but there are some variants that include bias correction steps or renormalization. These are statistical, rigorous models that you need to provide those assumed basis functions, such as linear and polynomial the inputs. Now let's talk about more of the problem and the context. I'll get into like the general methods that I've used to help improve it. First, there's numerical optimization. This is just a class of methods that are used to minimize objective functions. There's several classes within numerical optimization. This is unconstrained optimization that you might use for model training. Gradient-free heuristic optimization under uncertainty. This problem specifically has a large set of constraints, so it's best to use a gradient-based optimization with constrained solvers. This means that using the interior point method through IPOpt or sequential quadratic programming method APOpt is the best optimization for this. And there's also different problem classes that these solvers can solve, such as linear programming and convex programming, which are quite simple, but because of the nonlinear constraints and potentially conditional constraints, this is an integer and nonlinear programming method. I'll mention that the package that I do most of this research in is Gecko. It's a package maintained here at BYU, done for constrained gradient-based optimization as well as dynamic optimization. Now that I've introduced that, we're going to machine learning. This is a class of methods to learn from data and compress it into functional relationships into parameters and structures. And this is very popular in data science and scientific computing in general. There's different classes and different tasks for this. This specific problem is supervised learning in that there's labels. I'm trying, the property models are predicting properties of the glass from composition of the glass. It's regression, since it's predicting numerical values, not labels or anything. Finally, there's uncertainty quantification and propagation. Now, there's two sources of uncertainty that are considered in this problem. There's one, epistemic or model uncertainty from model parameters. This kind of models the model mismatch between the predicted values and true values. And two, there's uncertainty in the inputs. These need to be propagated through the system to get distributions for the outputs. And both these uncertainty quantification sources are used as intervals for constraints, which is a bit more of a unique method that I've seen in the literature. I haven't seen many other optimization problems do this, but they use uncertainty intervals as buffers or conservative steps from each constraint value for each property. Now that I've introduced all the concepts of this that I'll be talking about, let's get a quick overview of what I've done for this problem. First, I fit a series of machine learning models to composition property data. I then you interface these models, develop interfaces between the models and Gecko, the optimization package, this constraint optimization, to solve this optimization problem for low activity waste and high level waste. And then I've also found uncertainty quantification methods that pair well with these machine learning models, as well as different ways of doing uncertainty propagation for the algorithm that makes it much faster to run. This is just a summary of what I've just said. Again, I've interfaced the models. I've replicated these both low activity waste and high level waste algorithms within Gecko. I have implemented analytical alternatives for uncertainty propagation for a 10 times speed up for the high level waste algorithm. And by using more accurate models, I've seen for low activity waste, much higher waste loading from 34 to 37.5%, and 37 to 37.6 on average for the high level waste problem. And I'll get into each of these specifically as I go through my presentation. Now that I've gone through the introduction of the problem and some of the topics I'll be talking about, I'd like to quickly talk about just the general field of scientific computing and open source models in general. This is a part of a publication I did with Dr. Hanford in 2024, where we looked at directions of open source, free open source software, and where they're going. There are significant trends going of research communities moving from closed source software to open source software, and people are using Python much more than MATLAB, Simulink, and there's more use of these modeling packages like Pyomo, Viscosity, and Gecko. Like I said before, there's shift from low level to high level code. So people are moving from C++, MATLAB, some of the older codes to Python, which is more high level, closed source to open source. There's also been an explosion in the use of generative AI, such as ChatGPT and other large language models. And in addition to all that, since all these tools are open source and maintainable by the general public, there have been frameworks that both extend and combine and build upon these sources that are made widely available to the public. These are just some of the primary packages that are relevant to my project in both machine learning and algebraic modeling language groups. So for machine learning, there's scikit-learn, which has a series of machine learning models to train, and then TensorFlow and PyTorch both focus on deep learning models. And then algebraic modeling languages, which are equation-based and differential equation solvers. There's Gecko, which I mentioned before, as well as Pyomo, Viscosity, and Jump, which is available in another coding language known as Julia. In chemical engineering specifically, you would be using some of those machine learning packages I mentioned before for empirical modeling, dynamic models such as control, forecasting, and twin. There's also novel areas for use cases for generative AI and computer vision for anomaly detection and other applications. There's also equation-based modeling, which you primarily use for first principles models, where you have equations that describe the system, as well as model predictive control, dynamic optimization, parameter tuning, and a lot of other sources. Now, where this fits into my project is I'm taking these empirical models and machine learning packages and developing these empirical models and then interfacing them into an equation-based framework to solve the low activity waste, high level waste optimization problem. So in a way, it's combining black box models, white box models, so it's doing a hybrid model. Now that I've gone through just the introduction of the problem and just an overview of the open source packages that I've used, I'll start to get into my specific contributions. Now this next section is part of a publication that I did in 2022, where I integrated machine learning models into the low activity waste algorithm problem. Like I said before, I'm taking model structure, learned parameters, and training data from these trained models and re-implementing them within the optimization framework. I'll only be talking about the optimization step for this next section, but I'll get back to the uncertainty propagation step. This is a survey of all the methods that I use for this specific project. There's Gaussian process regressions, neural networks, support vector regressions, and least squares models in machine learning. And then for uncertainty quantification methods I use, I looked at ensemble uncertainty, model-specific uncertainty methods, conformal prediction, and the delta method. I also looked at tree methods, but I'll talk about that towards the end of this presentation. Real quick, before I get into each of the specific models and why I use them, let's talk about just interfacing these machine learning models into optimization. Because as available in the scikit-learn and PyTorch packages, they're black boxes. You just feed it data and tell it to predict, and it can do that. But to interface them into Gecko, into the equation-based framework, I had to peel back the black box so and understand these models. Now, what makes them compatible is if their prediction function is differentiable and compatible, since Gecko uses gradient-based methods. And this prohibits some models and architectures like k-nearest neighbors from being compatible, since some operations like sampling or sorting may not be differentiable. And additionally, some of these models, if they're too large, they might not be compatible with Gecko, since there is some computational overhead in solvers that it uses. I'll really quickly start with Gaussian process regression. This method fits a Gaussian random process to a data set with kernel functions. It updates prior to a posterior by adding the data. This animation I had here is one I made in the class a while ago, and just showing that distribution of infinite functions updating to a posterior as you add more data. And then after you have that posterior, you can train the hyperparameters to get it actually fit the data. This method is nice in that it can produce uncertainty quantification intervals in the form of confidence intervals, which a lot of methods in machine learning don't do natively. However, it is non-parametric in that it remembers all its training data and can become quite expensive for large training sets and prohibitively expensive for optimization. And I'll talk about that as I go on. Another method, so Gaussian process regression uses kernel functions to, as like similarity metrics, this is a radial basis function to compare between training points and the new prediction points. And another method that uses kernel functions is support vector regression. This model expands the data into an infinite dimensional space and then fits a hyperplane in that dimensional space. And like Gaussian process, it's non-parametric in that it remembers all of its training points, but not all of its training points, but it only saves a fraction of them as support vectors. So at evaluation, it can be a bit faster. Unfortunately, it does not produce the uncertainty quantification that Gaussian process regression does. Finally, I'll talk about neural networks. Neural networks are very popular in the data science community. They're the backbone for large language models and other deep learning applications. And just in a sentence, they're models that are composed of compositions of linear layers with nonlinear activation functions. They're very customizable if you have data for them. They can be used for regression, classification. They can predict uncertainty if you have the right loss function. As long as you can define a loss function and you have data for what you're trying to predict or characterize, you can train on neural network pretty easily. Now that I've gone through the machine learning models, I'd like to talk about some uncertainty quantification methods. Now, least squares and statistical models provide theoretical based and rigorous uncertainty intervals, which is nice, but some of these models that I just introduced don't have them inherently. So there are a suite of approximation methods that can be paired with these models to produce those confidence intervals. But since they are approximate, they can't necessarily be trusted from the get-go. So an important metric to consider is these parity plots and calibration plots to show if these intervals that are being produced by these methods are too underconfident or too overconfident when compared against the training set. I'll start in the methods. Probably the intuitive method for uncertainty quantification is to train multiple models and evaluate the mean and variance of the prediction of all those models. And this is employed most often as like bootstrapping or some other method. But unfortunately, while this works well for just prediction and giving intervals, it can be quite expensive to interface into optimizations because of the computational overhead. These large ensembles might be too expensive to run. Let's skip the slide. Next method I'll talk about, I referenced it a little bit before, is model-specific uncertainty methods. Some models, like least squares or Gaussian process regression, provide variance predictions, which is nice. And neural networks can be trained with on a Gaussian likelihood loss function to produce confidence intervals as well. And I'll get into the neural network specifically towards the end of this presentation. Finally, informal prediction is another method. It's more of a novel method. It uses minimal assumptions, and it's a set-based comparison method where it compares new prediction points to a calibration point with like a similarity function, and it's used to assess how close that prediction point is to the trained data that was seen on to produce confidence intervals. When paired with a singular model, it will just produce static intervals, which aren't necessarily desirable, but it can be used to calibrate or improve ensemble method, which I discussed previously. Finally, there's delta method. This is the same equation that's used for least squares models uncertainty quantification, where it's the inverse of the covariance matrix of parameters. And this can be theoretically applied to any model. Unfortunately, large parametric models like neural networks, that inverse of the covariance matrix can become intractable. So an approach to this is to do like a paired model method where you have a more accurate machine learning model as prediction, and this delta method linear model producing uncertainty in the background. And the only way to evaluate if this is trustworthy is, again, look at those parity plots and calibration curves. Now that I've gone over all the methods, I'd like to talk about some of the results for this study. First is just the model prediction accuracy. This is for the melt electrical conductivity property at 1200 degrees Celsius. Again, this is constrained for it to make sure that there's proper processing behavior of the melt during vitrification. And these models are all the machine learning models that I just discussed are paired with the uncertainty quantification methods and compared against the partial quadratic mixture model. And as you can see, all of them do better than the baseline model. These were done with 5-fold cross-validation, which is why there's bars in all of them. But yeah, so I was able to show with just this plot and some other plots that all these models are much more accurate than the baseline model. Looking at uncertainty, just to see if they're trustworthy, the ensemble method is very overconfident. I mentioned that before, that large ensembles aren't exactly compatible. So in order to make this work, I had to use a small ensemble, which didn't produce the best results. But most of the other methods produce very calibrated uncertainty curves, which is what you want to see. Finally, these are the optimization results implementing these machine learning uncertainty quantification models within the low activity waste algorithm. The dotted line is the baseline of solving with the partial quadratic mixture model, and the goal is to maximize waste loading of the glass in the vitrification process. And compared to baseline, most of the models do produce a much higher waste loading, which is desirable. I believe in this study, when I did it with Kyle, we decided that the Gaussian process regression with conformal uncertainty performed the best because it was one of the most accurate models with the most trustworthy uncertainty quantification methods, and it led to a higher waste loading. Looking at the solve time graph, it's pretty obvious that none of the models can really compare to the linear models because some of these are non-metric and non-linear. However, the neural networks are probably the most comparable in speed. But yeah, just some key takeaways of this study. I was able to show that machine learning models could predict this property electrical conductivity better than the baseline partial quadratic mixture models. I was able to show a suite of uncertainty quantification methods that exist for machine learning and interface them as well within Gecko. I interface both machine learning and uncertainty quantification within an optimization framework. And by applying all these tools that I developed, I was able to increase the expected waste loading from 34 to 37.5 for this example low activity waste study. Now that I've gone over the optimization step a little bit, I'd like to talk about the uncertainty propagation step, which is the second half of the algorithm. And this was a paper that was just published, I believe, earlier this month. That I was working on for last year. And I will get into the baseline method in a second. This is looking at how to propagate uncertain input distributions to output distributions, and then use those output distributions to inform the optimization. Just a quick recap of the problem and the characteristics of it. It's a very large dimensional input space to this problem. There's around 180 non-zero inputs going in this mixing equation and algorithm. There's a nonlinear input-output relationship between the property models as well as the mass balance. And some of the input distributions are non-normal. They have these triangular distributions known as PERT, which are similar to the beta distributions. So some of the straightforward approaches may not be applicable. And again, these the uncertainty from the input is propagated through the system to get output distributions, which are then used as intervals to inform the optimization to act as buffers for constraint values. The baseline approach that is used for this is to use Monte Carlo, which I'm sure many of you are familiar with. For uncertainty propagation and risk analysis specifically, you assign a bunch of distributions to those inputs and sample from those distributions and evaluate the system thousands of times. And because this is a sampling stochastic process, it needs thousands of function evaluations. This isn't necessarily compatible with gradient-based optimization, so there needs to be a clear scheme between the optimization step and this uncertainty propagation step. And even though it's not compatible, it is very accurate as long as you have but it can be slow because of that iterative scheme. There are some methods of improving it, such as using quasi-Monte Carlo methods, like sampling with syllables or Latin hypercube, which are low discrepancy sequences, or even sampling from a dimensionally reduced subset, which doesn't necessarily improve the speed or convergence of it, but I'll show it can prove that accuracy for dimensionally reduced methods can achieve the same accuracy as the full method. Now implementing this for 20 characteristic waste clusters for high-level waste, we can see by adding uncertainty intervals to the optimization problem, as we expect, the potential waste loading can decrease by a little bit for some of the waste batches, which is the optimization solver being more conservative with uncertainty. But we can see also that adding that composition uncertainty step with Monte Carlo is much slower. So running with no uncertainties or just model uncertainty, the optimization problem can evaluate on around 10 to 20 seconds. whereas adding that propagation step increases the solve time to on the order of 100 seconds. Now that I've introduced the baseline method, I'd like to talk about some of the methods I investigated to try to replace it. And these methods are analytical in that they can be described with equations and written with within the optimization problem, so that there isn't an iterative scheme just solved all at once with optimization. The first method is to apply a Taylor series expansion to the system and propagate the variances through the system of partial derivatives. This works well for well-behaved linear systems. Unfortunately, this is a very large dimensional problem, and that the evaluation of those partial derivatives can be quite expensive. In fact, just trying to do that naively, the method is just intractable within current solver and optimization problem. However, I'll talk about a method to decrease the dimensions in a few slides that makes this method possible. The second method is to use some of the tools I discussed previously, the data-driven tools, to train a model on the Monte Carlo process. This involves generating data by perturbing all the input parameters to this algorithm with Monte Carlo, and then using a data set to train a model, and then interfacing that model into the optimization problem using the tools that I just previously described in the last section. Both of these methods are made a lot easier and a lot faster with dimensionality reduction through sensitivity analysis. The method that I use is global sensitivity analysis through Silva's method, where orthogonal Monte Carlos are done in the system for each input dimension, so 180 simulations need to be ran. And this allows to do, the method allows variances of the outputs to be broken additively into indices or impact coefficients of the inputs. And this shows, these indices show which input features are most contributing to the output variances. And when applied to this problem, it showed that of the 180 input dimensions for each problem, only 5 to 10 features actually matter. Now, this distribution here is for the electrical conductivity property as before, and when comparing sampling just 3 of those important features compared to sampling all 180, the distributions produced are relatively the same, which is good. So using these indices, I created a dimensionally reduced subset of the top, I think, 8 or 10 features for each property, as well as the free variables of the optimization problem. And I used that as input, which made the first order error propagation method tractable, as well as the circuit model method a lot faster and easier to train for this application. Now I've gotten the methods, I'd like to start getting to the results. This is just accuracy of these approximation methods. This left graph, series of graphs, is the distributions produced by these methods on one singular wave splash, while the right one is for on average all 20 batches. As you can see, for most of the properties, the distributions produced are pretty consistent. There is some consistent bias, like for the first order error propagation method in the conductivity property, and the circuit model method with the PCT lithium property. But on average, these do pretty accurately compared to the baseline Monte Carlo and quasi Monte Carlo methods. Now, when applying these to optimization, we expect hopefully these methods produce the same solutions as baseline. And for most of the batches, that is consistent. There are a few standout ones that may be because of the inaccuracies I talked about before, but on average, they produce about the same solution as the baseline method. However, looking at the solve time, like I said before, the sampling and Monte Carlo methods can take on the order of 100 or so seconds. These analytical methods, the first order error propagation and circuit model, take around 10 to 20 seconds, which is 10 times speed up on average compared to the baseline method. Looking at some of these solutions, like the compositions of the glass produced, besides a few outliers, the compositions are very consistent, and the active constraints of the optimization problem are also very consistent. Now, if accuracy is still needed, these methods, which are much faster, can be used as like an initialization scheme for the Monte Carlo, and then only a few iterations of the Monte Carlo considered propagation can be used for even a faster solution to the baseline, but still the same accuracy. Just a few key takeaways of this previous study. I was able to show that analytical alternatives for the uncertainty propagation step are 10 times faster and produce similar intervals and solutions. I was able to show sensitivity analysis to reduce the input dimension from 180 inputs to 20. And another insight I was able to show with the sensitivity analysis is that by breaking down the input features to contributing indices of the output, this is useful for future analysis of this algorithm. So if future researchers want to try to reduce output in certain intervals, they can look at these indices and see which inputs need to be changed or improved upon. Finally, I'd like to get in the last section of my study. Now, this isn't in a publication, but it will be presented at a conference in May and be used for future work at Pacific Northwest National Lab. In this next section, I do the same thing as the low activity waste, low activity waste machine learning integration, but I did it for the full algorithm of the high level waste, which includes 9 properties. And expanding from the smaller algorithm optimization problem to the larger one, introduced some new challenges such as scaling issues, problems with modeling specific properties, and some properties with some of the non-parametric models that were working best previously. Before I get more into this, I'd like to talk about the tree-based methods I talked about before. Like the other models, I was able to develop interfaces from modeling packages into Gecko and the gradient-based platform. And these models work well in Gecko. Unfortunately, at scale, such as the scale for this high-level waste optimization problem, they don't necessarily work the best. For example, random forests, which are ensembles of decision trees, just aren't compatible because they are ensembles that are expensive to run. And some of the decision trees and linear trees aren't as accurate compared to the models that I already have been training. But this tool is available just for wider use for other problems that may be smaller or more suitable for these types of models. And because there's a scaling issue going from the smaller low activity waste problem to the high level waste problem, model reduction was necessary. I looked at a few methods of model reduction by feature selection by eliminating the 64 inputs of the glass melt composition to 10 or 20. I looked at employing regularization through lasso, or LaSsoNet, correlation methods, and F-tests, and I was able to identify a dimensionally reduced subset of these input features to feed to the models to train. And now another problem with upscaling to the high level waste problem is with modeling the chemical durability property of the product consistency test of various solutions, known as PCT. In both the baseline models, the partial quadratic mixture models, and some of the naive decision models that I trained, there is a very consistent bias in the high response region of these models. To account for this, traditionally, they've employed a method known as conditional bias correction, where at a certain output value, they add a bias correction to account for that. But even with that bias correction, there is still a significant error in those high response values. While I wasn't able to necessarily solve this problem, I was able to show with a well-trained model with machine learning and quantification, I could produce intervals that cover those true values. Now, this is a neural network trained on the likelihood of a Gaussian function, so it produces both the mean and the variance of its outputs, assuming the error is normally distributed. And while it's not predicting well in high response, the intervals provided by this method do cover the true value, which kind of addresses the problem. Obviously, you'd want a model that just predicts well at those high response, but with the current data set, this is like probably the best working method. And looking at the calibration curve, it is well calibrated, meaning the uncertainty divided by it is trustworthy. Now I've introduced the models again. I don't have any other new methods besides the one that introduced previously, so I'll just get into the model training results. Since there's 9 properties now, there's a series of 9 graphs. This is comparing to the training and testing set among all the models. There's linear squared models, bridge regression, score regression, Gaussian process regression, neural networks, random forests, linear trees, and decision trees. In general, I was able to show that both Gaussian process regression and neural networks were some of the best performing on these models. Now, for some of the properties like the TCLP model, it didn't do as well since there wasn't as much data, but from the other data sets, there's around 1,000 or so data points and more that made these models train well. And comparing the best fit models to the baseline models, the partial quadratic mixture models, as they'll show that there is a substantial improvement in the prediction accuracy, especially for the probabilistic neural networks. Another scaling issue, like I mentioned before, is with Gaussian process regression. It's a non-parametric model in that it saves all the data, and with larger training sets, that wasn't very compatible with optimization, so I don't employ spouse Gaussian process regression methods, which only use a fraction training set. So there, the improvement in those model sets was not as substantial as the neural network. And yeah, just to reiterate, these Gaussian process regression models were identified as the best working models for the web-3 study. Yeah. Now, employing these model sets in optimization, I was only able to replace the product consistency test properties with the Gaussian process regression models for that model set. And then for the neural network, I replaced all the properties except for electrical conductivity and viscosity because the intervals provided were too wide for the constraints. But looking at the waste loading for replacing some of those models, for some of the characteristic clusters, the probabilistic neural network does a lot better than the baseline. And some it does a bit worse, but on average, it does a little bit better. Whereas the Gaussian process regression model set does about the same as the baseline. Looking at the solve time, even though the Gaussian process regression method isn't doing any better than the baseline, it's running much slower. And besides, a few of the batches, the neural network models are running just as fast as the linear parametric models. Looking at the composition distributions of some of the components of this, you can see that the composition range produced by the more accurate model subset, the probabilistic neural network, is doing much better than the baseline or the Gaussian process regression method. Now, some key takeaways of this last section is I was able to show that improving waste loading for this full high-level waste algorithm problem is also possible with more accurate machine learning models, but there are some scaling issues and challenges that need to be investigated, like I've just shown when scaling from an example problem to the full problem. I was also able to show that a model reduction is feasible and also necessary for this endeavor. That's the bulk of my work. I was conclude by reiterating my thesis. Most of my work, I took these empirical modeling tools from packages like scikit-learn TensorFlow and re-implemented them and interfaced them into a gradient-based optimization framework to solve these high-level waste and low-activity waste algorithm problems. I also implemented uncertainty quantification methods and uncertainty propagation methods into the full algorithm. By implementing these tools, I was able to show higher waste loading, maximal waste loading with the more accurate models, as well as by implementing the better uncertainty propagation methods, 10 times speed up compared to baseline. There's a lot of future work in this. There's a lot of P&L that is actively working on this for the next few decades, honestly. So there's a lot of work to continue from where I'm leaving off, such as improving modeling developments. I know there's a project in the works of improving some of these regression models with non-numerical data and filling in some data points that weren't able to be measured to try to improve the regression capability of these models. A lot of the glass data points are also shared between properties, so they make it a possible way to distill knowledge between property models or create even a multi-output model for some of these properties, as a lot of the data is shared. And another important effort is just to create explainable models and better feature input. A subset, which I kind of worked on in the last section, but it's still necessary endeavor to do in the future. There's also future optimization work to be done. Again, this is expected future work for this project, but it would be possible to not just have a set model at the beginning of optimization, but to learn these model parameters, so you can choose an optimal depending on the search space of the optimization. And that may be implemented in gradient-based architecture, but it might be necessary to go to gradient-free methods and learn how to satisfy all of the constraints of this optimization problem within those gradient-free methods while selecting the optimal model. That's all I have to present. Thanks for listening. Here's some of my publications, 3 being related to this work and a series I've done with graduate students here at BYU, as well as my internship. To acknowledge my committee, my advisor, the engineers and researchers at Pacific Northwest National Labs and Washington River Protection Services, as well as fellow graduate students here at BYU. Thank you, and that's all I present. I'll take questions now.
Go to stop the recording. Okay. Come on.